Yeah, hi everyone. Thanks for coming after these slow events. Today, very, very happy to have Vedran Brdar from Oklahoma State University. Vedran got PhD in Mainz University, and he moved to Heidelberg within Germany for his first postdoc. And then he came to US for his second postdoc in Berlin Lab and Northwestern University. And then he moved to CERN for his third postdoc. And as of January this year, he became the faculty of Oklahoma State University. So we're going to talk about short baseline neutrino anomalies. Please take your time.
Yeah, thanks for the invitation. I actually gave a talk via Zoom. I don't know if you remember or how much you were paying attention during those times, because roughly 3 years ago, I gave a talk on gravitational waves. I think Mateus was still here, and he was the official person who invited me. I remember pretty well the date when I gave the talk because I was still at Fermilab, and several of you asked me about the rumors about G-2 announcement. That was exactly when the G-2 was announced, the 4.2 sigma anomaly. So I think it was roughly 3 years ago. But today I'm actually going to talk about completely different stuff. And basically going to summarize some of my work on the short baseline neutrino anomalies, and also give you a present, overview of the community of what's going on in that field, because that looks like something it's like an everlasting story, and it might soon be converging. So I want to start with the slide. Okay, this can be moved, right? How about here?
You can hit more. It goes more and hide.
There are several heights. That one? Okay, cool. Yeah, my first slide is the neutrino oscillations. And since I'm talking about the anomaly, there are several anomalies which eventually became a Nobel Prize. It's like neutrino oscillations is one of the examples. It was discovered in atmospheric neutrinos first in 1998. And this was confirmed by Snow experiment using solar neutrinos. But for instance, solar neutrino problem was there for years and decades, and eventually it got resolved. So maybe some of the stuff I'll be discussing today is going to converge and be eventually some established phenomena, or maybe it will just go away, like many anomalies in this in our field go away. So you never know, but you need to study and look into these things to understand things better. So yeah, the neutrino oscillations are quantum mechanical phenomena, and this is just the formula for oscillation between two flavors. Things just trivially extend to the three flavors, but I'm actually gonna indirectly use this formula several times during the talk, because there's going to be some sterile neutrinos also involved, and in that case, the simplified two-flavor formalism is applicable. So this is just mixing angle, and also the oscillation probability is proportional to the sine square of the involved med square differences between neutrino species, distance of neutrino propagation, and this is divided by neutrino energy. Since we're in the US, I will start this survey of neutrino anomalies with those based in the US, and first part of the talk is mostly going to be devoted to the MiniBooNE experiment. But the story actually started at Los Alamos National Lab around the year of 2000 with the LSND experiment, which was a stopped pion source experiment producing muon antineutrinos from the pion decay, and at a distance divided by energy of roughly 1 kilometer per GeV, they observed a significant amount of electron antineutrinos. And looking at the previous slide, this looks nothing but neutrino oscillations. You start from muon neutrinos, you end up with electron neutrinos. It looks pretty reasonable, but actually the magnitude L over E, it's too small, and when plugged into the formula on the previous slide, oscillations would not be able to develop across these kind of distances and energies. Actually, the LSND experiment was conducted during the roughly during the times when the Kamiokande did their measurement on atmospheric neutrinos. So now in retrospective, we know that this is an anomaly. At those times, I guess things were still pretty confusing. This is the main plot from LSND. maybe you can ignore the blue, which is the fit using some BSM model, but the data is here, and it rises over this standard model background given in red and green, and it's a 3 sigma effect. This was enough of a motivation for people at MiniBooNE to conduct the experiment. To start with the MiniBooNE experiment at this program at Fermilab. So MiniBooNE basically was designed to verify the LSND anomaly roughly at 10 times bigger distance and 10 times bigger energies. So L over E was preserved. So MiniBooNE reported the anomaly on 3 separate occasions, I think in 2010, 18, and 20. And in the last occasion when they did that, they reported the 4.8 sigma excess, and they were a bit more careful in phrasing than the LSND people. They didn't say that they see the excess of electron antineutrinos and neutrinos. They call it the electron-like event excess, and then it's up to you to interpret this. Of course, if you have more electrons in the detector, this could have come from excess of neutrinos coming in and doing the standard model charge current scattering. But combine this 4.8 sigma and 3 sigma from LSND and assume the statistically independent measurements, you will reach a 6.5 sigma, which is a pretty intriguing number when it comes to searching for new physics.
Meaning straight Nui bar and Nui bar relation, right?
Nui bar too?
I mean, mu to Nui, right? Within which model you combining?
It's when they report that, they always do the fit to the usual EV scale sterile neutrino.
Okay, so it's a
scenario. Yeah.
Not just the straight mu to Nui, right?
Well, in MiniBooNE you have both NUI and NUI bar access, right?
I just didn't understand it was within the sterile neutrino.
Okay, but
you could do like, okay, I disregard anything else.
Yeah.
And I just look at mu to Nui oscillations.
Right. But then you don't need to fix a model, right? You have the data and you have the prediction using the standard model processes, whatever is there. And this would be kind of that discrepancy, right? And then when you put in the model, sterile neutrino, then at the best fit point of sterile neutrino, you can probably explain the anomaly. So this would basically be, I would say, the difference between the data and the predictions within the star model. But actually my talk is about that. So
when you say it's not concerned about, do you mean using the MNF parameter? You have to use mixing parameters, right? Or no?
in principle, but here there will be, as I said, that this kind of distances, the oscillations, given the known mass square differences of standard model neutrinos, the oscillations don't have time to develop. So some of the mixed angles that will show up later and turn out to be significant is, for instance, the extension with sterile neutrinos when I put in some new mixing angles.
Okay, so you really shouldn't see any, or almost any.
Right, but there will always be some contributions, and I'm getting there. I'm going to have a detailed discussion on MiniBooNE, so please keep on going asking questions, and I hope I will be able to answer. So yeah, just to, since I'm already on this slide, just to illustrate this axis from MiniBooNE, this is low energy axis, where on the x-axis is the reconstructed neutrino energy. And here's a schematic picture of MiniBooNE. Is the experiment that works more or less in the same way how all the other similar acceleration-based experiments work and will work, like DUNE is going to work on similar principle. It boils down to accelerating protons, hitting them on some target. You produce a bunch of particles, some of them pions, kaons, and this kind of particle can decay to neutrinos, and then neutrino just goes to the detector and it does something in the detector. So yeah, let's talk about these contributions in MiniBooNE. Now I think I'm answering your question on this slide. When they say that they report the electron-like event excess, these are the shower events which can be produced from several different final state scenarios. For instance, if you have a scattering in which you have just one electron in the final state, that works. That would go into this anomalous channel. What would also go is the case where you only have one photon, because MiniBooNE cannot distinguish between electrons and photons. Photons in this material, and this is the 6 meter diameter mineral oil, photons in this material will usually propagate roughly order half a meter, and then pair produce the electron positron, and the MiniBooNE cannot distinguish between those two. What also works in principle, if you have a collimated E plus E minus, you know, each of the electron would induce its own shower, but if they're very collimated, given the resolution of the experiment, I can be in a situation where I only see one, and then that would enter also in the anomalous channel. And finally, again, since you cannot distinguish electron and photon, collimated gamma-gamma also works. So, so in the standard model, the majority of the events relevant for this MiniBooNE anomaly are these 3 channels, and I'm gonna come back to them later. First one is the charge current NUI events. So you have electron neutrinos, which are also to some extent produced at the source. They come to the detector and they can scatter and produce an electron simply through the charge current process. And that would be this kind of topology here. This electron here would do a Cherenkov radiation, and you would observe the Cherenkov cone inside as a signal here. What can also happen is the neutral current pi0 production. The neutrino-nucleus scattering, what can happen is that pion odds speed out, and that one would directly decay promptly to gamma-gamma. And then I would basically have collimated gamma-gamma case. That's actually shown here, where you can see that each of the photons would eventually give its own Cherenkov rings after being converted to E plus minus paired. But in some situations when they're very collimated, MiniBooNE may not be able to distinguish between two. There will also be many events where pi0 will decay to maybe, you know, if it didn't produce nearly at rest, it would decay to back-to-back photons. In those cases, I would see 2 showers, but yeah, that's not the anomalous channel that I'm talking about here, but that's also something that MiniBooNE uses, and I'll discuss later. And we also have another option, which is the neutral current gamma production. So in neutrino-nucleus scattering, when it's really not elastic, you can also produce various GeV scale resonances, which are very short-lived. Like one of them, the one that contributes the most, is the delta 1232. So this is the energy. And that one can decay to photons. It usually decays to pions, but sometimes it will decay to photons, and when it decay to photons, then I'm interested, because that's the anomalous channel. This was a brief review of these 3 processes, and I'm going to discuss in a moment what I actually did about that. And now I want to kind of introduce the story and my motivation in this part of the talk. So scattering neutrinos or nuclei, it typically requires the usage of Monte Carlo event generators which have implemented nuclear models. Scattering on nuclei is much more complicated than scattering neutrinos on free protons. That's something you can do on a piece of paper. But in the nuclei, many sorts of processes can happen. Even in a very simple processes which look like quasielastic, you can have some pions which is emitted and then immediately reabsorbed. So to take into account all this stuff and the proper kinematics, the experimentalists, it's state of the art that the experimentalists use the Monte Carlo event generators. And MiniBooNE collaboration actually used this nuance event generator, which is not anymore supported. They used it throughout the whole operation. It's not anymore supported, and it means that at the point that they used it, it harbored relatively obsolete nuclear physics models, whereas in the meantime, there's been much more developments, and actually the modern neutrino experiments, such as T2K and NOAA, for instance, they use mostly GeNE. GeNE is the most popular Monte Carlo event generator in neutrino physics, and I believe that majority of the collaborations are actually interfacing with that one. There's more. So there's also GIBU here, the German project, which is based on some complementary principles to Gini. And we also made use in our work of Nuvro. Nuvro is the Polish project, which is basically usually it's often like a sandbox for Gini, like a place where you first test the models and then later you pass it to Gini, which is usually linked to most of the neutrino experiments. Creators of Nuvro in Poland, I think they're also very active in development of new nuclear models, so they have their own facility to test for that. And Gini here in the versions that we used came in 6 different versions because, you know, there are different model parameters and sometimes they tune to different data. So there are 6 different tunes which they put out in that version, which is 2022. So my strategy here, given what I just told you, in our work, we made the predictions first using nuance, the one that MiniBooNE used, followed the MiniBooNE papers and performed various cuts and selections for the 3 processes that I told you about, CC, NUI, pion, and the single-photon. And then after doing all of that, we make a comparison to what MiniBooNE actually reports. And then we do a bin-by-bin tuning of any possible differences that may arise. And then what we do next is simply repeating that procedure using the other event generators. And we also do the same cuts and same tuning factors as in step 2, because I want to make an apple-to-apple comparison at the end of the day between this nuance and these other generators. In other words, I want to make use of, I want to study the nuclear and hadronic physics uncertainties associated to MiniBooNE anomaly. And maybe if things are very extreme, maybe standard model can explain this 5 sigma effect simply by the fact that there is some freedom in nuclear and hadronic uncertainties that can lift me there. I'm not going to give you a spoiler, but this is where I'm heading to. And route, I will also talk about some BSM features. So just to illustrate that there is something going on here, and you don't really get the same results when you use the different generators. This is for the first process where the neutrino interacts with the nucleus, and it's the charge current process where the final state is only one charged particle, electron, and there's no other particles above the Cherenkov threshold, so I only see the electron. And comparing these peaks between different contributions of the generators, you can already see like at least 10–15% differences. So there's something going on already for this channel. And this channel is something that among those 3, I would expect it to be the most understood, because that's the charge current.
All the different Gini models or nuclear physics model differences?
Some of them contribute in fixing a bit on the nuclear model freedom, but sometimes they also tune to different measurements, because some other collaborations like T2K and Nova and Minerva have performed various measurements. And then this kind of gives them the idea where they should put in the parameters. And using different data, they can, you know, use different parameters, and this gives this kind of difference. So there's a lot of nuclear physics and some freedom swept under the carpet, but knowing some information from the neutrino scattering, because MiniBooNE is not the only experiment where you can study the neutrino scattering. There's a lot of neutrino data. You can use that as an input for your studies and fixing those models. So I'm just going through these 3 processes, right? Now on the process number 2, that was the neutral current pi0 production. And here I said that sometimes in the neutrino-nucleus interaction, you can spit out the pion, and pion would decay to 2 photons. And if photons are collimated, that I'm interested in. It goes in the anomalous channel. Also, if one photon, let's say interaction is very close to the edge of the detector, one photon leaves and the other converts inside of the detector, that's I'm also interested in. And if one is for some reason, one photon is very soft, below the detection threshold and one is visible, then I'm also interested in, because that would also give me one shower in the detector.
What's the vertical line below the?
The vertical line on the plot.
Yes. No, on the diagram. The one is Z and below it, what is it?
Oh, what is this? This is not my plot. I took this diagram from
What does I stand?
yeah, I don't know. I'm not sure if it's a particle representation. This is at least the Mandelstam T.
What's it? Must still be a Z.
Yeah.
No. You cannot have two Z properties. No, then it's zero.
It's something that talks to pion and Z. Yeah, I don't know. I honestly need to look it up. I took this diagram as a representation of, I didn't make this diagram. It just let in the neutrino-nucleus interaction you can spit out the pion, and I just stood. Yeah, sorry for not knowing what that is.
Sorry, clarification. You said at the top you said MiniBooNE prediction, but they also use nuance as well. So what's the difference between what MiniBooNE say they get and nuance? And
You said muons?
you said nuance. So I'm just trying to read you. The MiniBooNE prediction is, I'm looking at the top right hand part. Works for that one too. Okay, you have at the top of your
Okay, the MiniBooNE prediction is the one that in this case would corresponding to the nuance analysis.
right, but then you have another plot which
Okay, here. Yeah, here the MiniBooNE prediction is the official prediction, and here the nuance diagram would be prediction before doing the final tuning, because that's the difference that we find before doing the actual tuning. But then we do the same factor for.
The tuning is with a physics model or with the detector performance?
It essentially quantifies the fact that it also includes the reconstruction of the energy in the detector and any sorts of imperfections that we might have missed, for instance, not doing the real detector simulation.
Okay, so it is quasi really without the real detector simulation.
Yeah. In our case, we are users the event generators, but we're not doing we're not like, we don't have the access to the full detector simulation from the collaboration. But that's still, I can still do the tuning across. This still allows me to study the nuclear physics uncertainties, the differences between nuance and all the other processes.
So what we should pay attention to is not so much the MiniBooNE and MicroBooNE prediction, but actually the comparison among different models.
You said MicroBooNE. I'm not yet there. So yeah.
So on that plot, you have a dark heavy line with MiniBooNE. But that has all the bells and whistles of the detector folded into the calculation. The other ones do not. And so the ones we should compare with the other ones. Do I understand correctly?
Can you allow me just to start saying, I never said anything about any of these plots. Can I just say something and then please ask anything what is unclear? Because I'm just not rushing here. First, I want to discuss this plot on the left. As I said, we're users of the event generators, and we can consider this process across different event generators. And this is what we do here. And this is basically using the event generators out of the box. And you can see basically here the agreement between several different generators. And the case of GIBU, it's somewhat underproducing this channel for pions. And this is known in the literature that with GIBU you don't get as many pions. And I'm not going to claim what is wrong, what is not, because these are different nuclear models. But this allows me to get a handle on the uncertainties that different models in the literature provide. So this is the using generators out of the box. This already tells me something, but this is not exactly how MiniBooNE gives their final word on what is the contribution from this channel. So they actually have a control sample in which they count pions. So topologies where they identify 2 photons. And that's what we use here. So this is something different than the bottom plots. This is the number of pi0 events as a function of pion momenta, where we have different contribution from different generators, but also here we make a direct comparison to the data. And this kind of information is then put in, and we use it to obtain what we call the data-driven predictions, which have the information on the pi0 production. And this is closer to what MiniBooNE is actually conducting. So here you can see the differences between different generators to be smaller. GIBU is still somewhat underproducing. And I will basically later discuss the anomaly in connection to both of these cases. So this.
Can I ask you also even simpler question? So you have some uncertainties at the production side, and this is a detection side, right?
Right.
The production side is whatever this PNB neutrino source does. There is another collaboration that uses the same beam, right? And that's microbeam. Does the spectra that they predict minimum of the neutrinos coming out of the production, are they the same? And to what degree of accuracy?
You mean you're talking about the flux uncertainties?
That's correct, yeah.
So for
So
the
there are at least two groups, right?
Yeah,
Independent, the independent.
Yeah,
right?
they're not.
I mean,
Yeah.
To what percent do they agree?
S-
Across different energies.
so I never studied MicroBooNE, so I don't know what is their strategy. But for MiniBooNE, as I recall, the uncertainties on the flux are relatively subdominant. I would need to check the exact predictions, but I don't think it has been discussed in the context of anomaly. So I think that the production side is a bit is under control, even though there's of course always some uncertainties in the process of pion decays. I'm already half an hour. Is it better, or do you have a follow-up question? Okay. So then let me just very briefly discuss this slide because it's concerning how slow I am. But I'm still happy that you're asking questions, because when people are, that means that you're interested. So this is the third process, the neutral current pi0 production. Neutral current gamma production, where you can produce some heavy GeV scale resonances like that delta 1323. There are several contributing. And here again we have contributions from using just event generators and also using the information on the pi0 production. How is now pi0 related to this photon channel? Well, this delta and similar resonances will in 99% of the cases decay to pions, and only in 1% of the cases will decay to photons. So MiniBooNE actually uses also in this case the pion production, and they also use the theoretical branching ratios for the photon decay for the photon channel from the PDG. And this is, for instance, shown in this plot here, where we take the PDG values and vary the contribution by 2 sigma. There are actually different values reported at different places, but we take the one from PDG, and we also looked into whether one can potentially explain the anomaly if I'm playing with these branching ratios for the photon production. So at this point, I redid the calculations of MiniBooNE, and I have my own calculations for these 3 processes, so I can make the analysis and see what's going on. And here I'm still following the MiniBooNE's procedure, and I'm working in the framework of 3+1 model with EV scale sterile neutrino. That's the leading, I mean, at least from the experimental side, it has always been the leading model how to explain this anomaly. So how does it work? You have your usual 3x3 Platonic mixing matrix, and now you extend it with the 4th row and column. And these 2 elements in red quantify the mixing between sterile and 4th species and electron neutrinos, and 4th species and muon neutrinos. And this basically allows me to go from muon to electron neutrino very efficiently across very short distances. The EV scale is not accidental. That is a couple of orders of magnitude bigger than the mass square differences in the standard model. So using that formula on the very first slide, I would have an efficient transition. So you can think of sterile neutrino as a catalyst for a very efficient conversion between muon neutrinos to electron neutrinos. There was a question toward the beginning if I use the standard mixing angle. Now I'm using non-standard mixing angles. These are These are new mixing angles which arise in the 4-flavor formalism. And then using our own calculations, we can make an analysis and find the preferred regions for this model in the parameter space of sterile neutrino mass and this mixing angle, effective mixing angle, and compare different generator predictions with this light gray, which is the official MiniBooNE prediction. And you can see that, of course, you see somewhat different lines because there are somewhat different numbers put in the calculation, given that for each generator, for each model we're having different predictions. I can show this plot and this analysis in the sterile neutrino versus mixing between sterile and muon neutrino parameter space. And here you again see the preferred regions in different generators. But here this plot allows me to also plot the global muon neutrino disappearance limit. You see, if you want to go from muon to electron, you're also sensitive to the cases where muon neutrino disappears. So experiments which are sensitive to just the disappearance of muon neutrino. And here the leading experiments are MINOS and IceCube, and they have set a pretty strong bound. And you can see that this line is to the left of these preferred regions. So there's a problem and there's a tension. I didn't invent this tension in this analysis. This has been found by people doing the global fits, and it still persists in this analysis. And we found that tension also with the present analysis and with the data that we found in computed for these 3 channels.
Is LSND
we haven't done anything for LSND. LSND operates at roughly 10 times smaller energies than MiniBooNE. And whenever we talk to people who are developing the event generators, they're saying that these energies using that kind of generators and integrating in this way is not very reliable. So we actually started with LSND, but turned out only working at GeV energies with MiniBooNE. So LSND is mostly around 100 MeV or so. Here I have a fit with sterile neutrino. It has a pretty reasonable chi-square over degree of freedom, so I can do the fit, but I have a tension when I put in all the data together, and I have a problem with IceCube and the MINOS, and in principle, when I put all the neutrino data together, this model has a problem. I'll come back to that.
I'm trying to think of how IceCube is the one that you don't know. How do you make the one?
So IceCube has a pretty good strategy because they have muon neutrinos at the TeV energies. And it turns out that for this kind of model with TeV scalar neutrino, inside of the Earth, you have a resonant effect for the conversion, for the disappearance of muon neutrino. If they didn't have that, they would probably not be as sensitive as the others. But unlike all the other experiments, because they're passing through the Earth, through the matter, and they have this resonant effect, and that makes the limit pretty strong. They already analyzed this with like 10 and 15, 8 years data. I think now they're doing the analysis for 15 years. I've showed you the fit on the previous slide. Here I'm showing the predictions in terms of stacked histograms, like in the case of MiniBooNE in the first few slides. I'm stacking the contributions from all these standard model contributions, and in dashed for each generator case, there's the contributions from sterile neutrino at the best fit points, and these are the best fit points. Sterile neutrino solves the problem if we just think about MiniBooNE. But again, there's this tension with all the data. And what you might be wondering if there's a explanation of this problem, a resolution of the MiniBooNE just by standard model without any sterile neutrino, because we did the new computation within the standard model. And that's to look at the significances on the last column. And they're in the most exotic, in the most dramatic case, they reach 3.1 sigma for this model with Nuvro, but they generally stay in the ballpark of 4 sigma or so. So with these calculations, we basically verified the fact that the nuclear and hadronic uncertainties don't seem to be the leading contribution for explaining the anomaly. That might not be the most extraordinary results, but it was not done before outside of the MiniBooNE collaboration. And here's the same for the Monte Carlo only predictions. As I said, these data-driven ones are something that is more close related to the experimentalist, to what they're doing, and the Monte Carlo is using the generators out of the box, but the results are pretty similar. What I just want to note on this slide is that there is we were here able to implement this variation of branching ratio for the decay to photons. And if you look at the respective numbers here in the last column, it's not a game changer. So even varying this by 2 sigma, it doesn't help too much in explaining the anomaly. So the conclusion from this part of the talk is that the standard model, nuclear and hadronic uncertainties, don't seem to resolve the MiniBooNE anomaly. And at this point, I can start to think more about BSM. This now really motivates various BSM scenarios. And I already told you about one, right? I did this analysis in the framework of EV scale sterile neutrino. That's the oscillatory explanation, but there's also many non-oscillatory explanations that have been performed in the literature. For instance, one is here from Maxime. I think I found this paper with Ryan et al. Here in 2018 on the magnetic moment. And this is not an exhaustive list of papers. There is this is taken from MicroBooNE presentations during the time when they put out their first results.
Yeah, can I ask you for a previous slide? The fact that delta, some of the deltas are inside the carbon nucleus, doesn't matter. Yes.
Some of the deltas.
Well, the neutrons are inside the carbon, right? It probably doesn't matter, but I just wanted to know that you just assume that we went about it.
Yeah. So.
Deltas are very wide. They're not probably making out of little carbon nucleus. They decay right inside. Whether this
so pions, as being longer lived, they are in the final output. So just as a user of the generator, not as a nuclear physicist, I want to evade the question, but try to answer. With the deltas, they're being decayed already, and any kind of photon coming from the delta is going to appear in the each event description on the generator side. So I'm not the expert of what is actually happening with the deltas, but they're being treated with the generator, and when the photon comes out in that process, then that's something that I select, because I see a photon and I can see that it's coming from the delta. But what the dynamics of the delta itself, this is not what I know too much about, honestly. Right. So yeah, I said that there's many non-oscillatory explanations, and that would be something where you don't have oscillations of MiniBooNE neutrino. So let's say MiniBooNE neutrino comes all the way to the detector, up scatters to right-handed neutrino, and right-handed neutrino decays to neutrino and Z prime. So you have a certain exotic model, and Z prime, because of the master kinetic mixing, decays to E plus E minus. And if these E plus E minus are very collimated, that counts as an anomalous event. This is just taken from one of these papers here, one of the strategies for the non-oscillatory explanations. Some of these explanations are already under tension. Some of them are very exotic, but these are also several valuable explanations and directions of tackling the MiniBooNE anomaly beyond the traditional channel that collaborations are following, and those are the mostly using always this EV scale sterile neutrino fit. Okay. I thought I had yeah, okay. One slide I reshuffled recently. Okay. Now I want to, in the next few slides, actually, I'm not sure if I should skip these next few slides, because I also want to talk about the gallium anomaly. So there's been a lot of questions about how are we going to handle the time? Because I don't want to, abuse your hospitality and keep you here until very late in the afternoon. So I don't know if I should skip. I could, in principle, skip the next 3 slides, or I can just, yeah, I don't know if I can say it in few words. But in this recent work with several colleagues at Fermilab Northwestern at Oklahoma State, we basically found a way how to save how to make the model with stellar neutrino, the oscillatory explanation for the MiniBooNE, more consistent than in the vanilla case. And to remind you, vanilla case would be this one here, where I need to acknowledge these strong constraints from the disappearance. And what we made use of is the energy dependence of PMNS matrix element and the fact that neutrinos don't energy scale for neutrino production and detection can be different. In a nutshell, we're using the fact that different neutrino experiments perform their analysis at different energy scales, which allows us to saturate, for instance, the limit here on this mixing angle. This is related to 1,4, just is a sign, the sterile neutrino mixing angle, at the reactor experiments, which are most strongly constraining this parameter. And then I let this parameter to run between MEV and GeV scale, and MiniBooNE is a GeV scale. So I can pick up larger values of the mixing angle at the GeV scale, and this gives me a bigger probability for.
Do you need some light mediator?
Yeah, in this case, we have sterile neutrino interacting with Z prime. And we need a model where the angles actually run up. And this happens in such a scenario. If we had a scalar, the running would be with the opposite sign. This sign of running can actually be understood in the QED, where electron mass would also be running to smaller values in the QED. As you approach the gut scale, electron mass also goes down. I never had an intuition for that, but we also made a comparison. For instance, in Weinberg's book, it's quoted that this is just a comparison. We did our own RG calculation for this particular model. And so Z prime needs to be relatively light and not integrated out. So let me see. So let me try to remember. It's this is starting from MEV to GeV. So Z prime should not be should be around the MEV or so, or lighter. It needs to be relatively light. If I have Z prime which is very heavy, I integrate it out very early on and doesn't have much effects later. This may, in principle, we didn't study the cosmology of this scenario.
Maybe this best for the couples, not to the last.
You need to have relatively large couplings because you're already loop suppressed, since this is RG. So the couplings needs to be relatively large in this kind of scenario. Basically order 1.
It sounds like you're getting into problems with your synthesis, right?
Yeah, really.
I mean, it's very light specified.
Well,
first
you
you have
don't
the
worry about cosmology in any case, because it's one of the.
By the way, yeah, I was just about to,
Regardless of Z prime.
Well, no, if Z prime was really heavy.
But
No, you would still populate the absolute 100% this sterile neutrino.
Oh, maybe.
It's just Z prime there's nothing to
Yeah,
do with that
that's
story. Z
populate-
prime is just to make this weird running, right? But the problem is
Depends when they decouple though.
right, so EV scale and neutrino, I need those mixing between sterile and muon and electron to be order 1, and this is thermalized, and you get 4th degree of freedom. You get an effective equal 4.
You're dead on arrival.
You're dead on the arrival, but interestingly, we didn't explore this because this paper was not about cosmology, but people have actually tried to explain this problem with this kind of particle, because if Z prime is abundant and existing in the early universe, you can use it as a new matter contribution for the potential. And then you decrease the mixing angle in the early universe. And then simply because of this new contribution to the matter potential. But that was proposed, but that didn't work out. With more recent data, that is not anymore on the table.
Lots of epicycles.
But now you also, in addition to the 4,
Secret interactions, yes.
in addition to the 4, now you've got another engagement present as well.
So this is to address the anomalies, but admittedly, cosmology is not. It was not in the ballpark. And just to illustrate the level of improvement in the mass versus mixing between muon and electron, this vector mixing, comparing the standard preferred regions from MiniBooNE and what I can get by using the other experiments on the constraints of those two relevant mixing parameters. And now with this running effect, I can improve things a bit and get this RG correction, which is, this RG line, which is much closer to what this MiniBooNE's preferred islands. So yeah, that was one way how to tackle this problem, but yeah, and this is basically my BSM input on MiniBooNE here. So I want to say that things are still ongoing, and I'm not resolving the problem here. So currently at Fermilab, there's a short Baseline Neutrino program going on, and there are first results from MiniBooNE, which are not in. They're not confirming the results from MiniBooNE. They're in tension with that, but there's more data to be analyzed. So MiniBooNE is not taking data anymore, and yeah, there's only data to be analyzed. But Icarus is taking data, and SBND was just recently installed. And you see that the presence of these three experiments will also have a very convincing final words on the EV scale sterile neutrino, because you can basically test the appearance across different baselines. And this was my final stuff on the MiniBooNE. So I basically first verified that the nuclear physics seem not to be jeopardizing the anomaly. Unfortunately, I would prefer that it just solves it. And I told you about some non-oscillatory explanations from the literature, and also sterile neutrino, and also how to alleviate the tension with sterile neutrino with this running effect, which is admittedly very likely in tension with cosmology, as is the vanilla model. So I want to skip these two slides in the interest of time. This is about reactor anomaly, which I never worked on, but since I'm discussing the short Baseline anomalies, this is some anomaly that appeared in 2011, but with more recent calculations, following the recent calculations from the, I believe, nuclear theorists from the Russian Kachanov Institute. These fluxes of antineutrinos from reactors have been re-verified, and currently the reactor anomaly seems to be fading away. And yeah, this is one of the long-standing anomalies that seems to be going away.
Well, there are also some crazy Russians with this neutrino 4 experiment. Right?
Neutrino 4 is not in my not in my ballpark here. I think that they have a very large mixing prediction, which is almost
very sure.
It's you just looking at the experiments. I think unitarity. There's a problem with the present unitarity constraints, and also I think Giunti did the analysis and found what's going on with that thing. So I'm not really taking that into account. But actually, okay, I still have officially 10 minutes. Maybe I'll go 5 minutes longer. I want to tell you about gallium anomaly and some because that's been something very recently popping up in this business. So just for those of you who are not familiar with that, the gallium experiments, neutrino experiments were GALEX, GNO, and SAGE. GALEX and GNO were based in Gran Sasso in Italy, and SAGE was in Baseline lab in Russia. And these were gallium experiments which were mostly dedicated to detecting solar neutrinos. Actually, I believe that GALEX even pioneered the first detection of PP neutrinos. For their calibration purposes, they also had the measurements where they put the radioactive source in the heart of the detector. And this radioactive source, chromium-51, would spit out neutrinos, and those neutrinos can interact with the gallium material. Here's the process. Neutrino plus gallium gives you electron plus germanium-71. And then you need to start to count the germanium atoms. So they have the measurement versus prediction from 2 data points from GALEX and 2 from SAGE. Admittedly, SAGE used argon in one of their studies, not chromium-51, but in all other searches, on all other tests, the chromium was used. And you can see that they have measurement or prediction, something like 0.87 plus minus 0.05. It's a 2 sigma effect. And it's nothing to be worried about, but this has been going on in the literature for a while. And people were aware of it, but with this kind of 2 sigma effect, in principle, you would not need to worry too much. But that statement changes actually very recent.
Sorry, just to interrupt you for a second. Can you go back? I want to make sure I understand exactly what you said. So they have a neutrino source right at the center, and they're measuring the range of neutrinos that they see from the neutrino source in their detector, and that range is too small.
Correct. They're counting germanium atoms inside of the detector, conversions from gallium.
Yes.
So it's they're trying to extract.
There's no solar physics or whatever.
There's no solar physics, but I just started this as they were in general solar experiments. And by the way, this new experiment that popped up, I believe that they're not even trying to do solar neutrinos. They're fully devoted to they were motivated by this 2 sigma tension.
And sage argon, is it like chlorine and argon?
Sage, yeah, it's basically one of the argon isotopes just going, I think, is it chlorine?
Is it a repeat of Davis?
No, I don't know.
Did Davis use that material?
Use chlorine? Yeah.
Okay. Okay, got it. This argon only appeared in that run of Sage. So somehow Sage also had the run with chromium. So I guess they were playing around. They had the access to several different radioactive sources. There might be, but you know, let me go to possible explanations. But before, just to see like why is this now more important than what the previous slide seems to imply. There's this Baksan experiment on sterile transitions. Very convincing acronym is BEST. So this is the BEST experiment. And it's being now conducted at the same location where the SAGE was done after some discontinued operations. And they're basically conducting the same experiment, only with chromium in this case. They have a radioactive source, inner target and outer target, 2 different chunks of material, and they have again they were able to do the measurements, and on top of the 4 data points on the previous slide, they added these 2 data points in red. These are much more precise measurements, and now when you take these 6 data points instead of 4 and combine everything into measurement over prediction, you get something like 0.8 plus minus 0.035. This is basically a 5 sigma effect now. So they recently claimed the 5 sigma effect. So it seems to be that you're predicting more than you know, you're over predicting. So what can possibly be an explanation of that? Well,
if the prediction from a theoretical calculation, there's no way I have uncertainties in my nuclear.
I'm going there because I studied that, so I'll be there very shortly. But before going there, what would be the main explanation how, given actually this talk, how to explain this, how to have less of a prediction and boost this number? Well, have some neutrinos going to sterile neutrinos, right? If that happens, sterile neutrino go and do nothing, and you just have that. But since the effect is now 20%, people did the fit, and in the mass versus mixing angle between sterile and electron, this is the preferred region at 0.3. This is huge and very unacceptable given the strong constraints from solar and reactor experiments that we have right now. So having the sterile neutrino in the story and doing nothing else it's not a good solution. So one needs to think more. So now to start to answer your question, we actually asked ourselves in this recent paper, we were asking ourselves like what can go wrong, like in this gallium measurement, and where to seek the explanations. And some of the stuff that I can tell you, like what can go wrong, they will even be in contradiction with the standard nuclear physics measurements. But I'm just going to try to explain like what needs to happen to explain the gallium, both within the standard model and beyond. So I'm starting with a cross section. This is the process which I showed you before, and the matrix element for the process in this direction is the same for the matrix element for the process in the opposite direction. And the process in the opposite direction is relevant because germanium-71 decays via electron capture, not via standard beta decay. So what the experimentalists actually do for the cross-section, they get the cross-section for this process as a function of the lifetime of germanium-71. So there hasn't been too many measurements of germanium-71 lifetime. The last one was in 86. That's this line in black here, 11.5 days. And there it's yeah, I don't know by heart, but you can, yeah, we can look it up later. So yeah, there are several measurements of the lifetime of germanium-71, and the one in white here with bigger errors, they come even from the 50s, 60s, and 70s. and they're sort of in disagreement. But if we take the black line, the effect is 5 sigma. But if the lifetime is 2 days longer, the effect would be 1 sigma, because bigger lifetime, smaller matrix element, smaller cross-section, and that solves my problem. The other very exotic state, which can in principle explain this, is having some new exotic states of gallium-71, yet discovered excited state of gallium, which of course has not been measured by nuclear physicists. But let's say if germanium-71 can decay to this new yet undetected states only in 20% and 80% to ground state, that would also explain the problem. These two proposals for the cross-section part were resolved recently because these two experimentalists, they read our paper and studied both of these options. Kolar is the guy who has a lot of germanium because he's looking at dark matter, light dark matter scattering. So they have a lot of germanium. So he studied the decay of germanium-71 and found confirmation of this old measurement from the 80s. So 11.5 days is now very firmly established. This is the measurement from this year. And these new exotic gallium states would, of course, de-excite and give you some extra photons. And those would be these lines like this one in red, yellow, and blue. And those also have not been observed in the data. So they can firmly exclude that kind of possibilities. So the cross-section doesn't seem to be the resolution of the gallium anomaly. And now let me go forward. Now I can think about what's going on with the flux. The flux of neutrinos is coming from chromium, and chromium-51 also, now I'm looking at chromium, not argon. Chromium-51 is also decaying via electron capture. So this is the relevant process where you have vanadium-51 in the final state. And they actually measure the source intensity calorimetrically. So it's total energy divided by energy released per 1 decay. And it's notable that in 10% of the processes, this reaction would give you excited state of vanadium, excited state with the energy of 320 keV, which would de-excite, and those photons would be the main contribution to the energy release, and they're using that to infer the strength of the source. This happens in 10% of all the 51 chromium decays, and here I just want to point out that if this number 10%, which has been measured many times, but there's some width, all the measurements don't agree with each other very well, but they're still around 10%. If this was like 2% larger, 12%, that would basically explain the anomaly. If the branching ratio was 12 instead of 10%. And another exotic point would be like if that energy of the released photon is not 320 keV, but a couple of dozens of keV more, that would also help in resolving the anomaly. This is very exotic to claim that the first excited state of vanadium would need to have 370 instead of 320 keV. This goes in the direction of maybe some new decay channels. I'm not committed to any of these solutions. I'm just telling you what would in principle need to happen to explain this through the flux. There's been
the 90% goes to ground state.
The 90% goes to the ground state, yeah. And I've seen like 5 or 6 measurements being reported. They cited by BEST. And they really don't agree with each other even within 3 sigma or so, because you see it's pretty wide here, this gray region. But you're asking about the details of how they're conducting those experiments, or yeah, I don't remember looking into that in detail, so maybe we can talk later about that. But yeah, the flux is very exotic, but I'm just telling you what needs to happen to explain this about flux. And now we come to probably the most likely explanation of the anomaly with the Standard model. That would be the germanium extraction efficiency. So you have like 50 tons of gallium, and you have order 100 atoms of germanium that are being produced in the interaction. So you need to extract that. And they're claiming that the germanium extraction efficiency is around 95%. They got it in the separate runs, where they put in some bigger chunk of germanium inside, and they want to extract as much as they put in. And this was in general working very well, and they're confident on this on this extraction efficiency. It's quoted 95 plus minus 1.6%.
So is this some sort of a solution or some salt or is this like solid state? What is it? What is it done? Like
How do they extract germanium?
yeah, like in Davis's experiment, there was like the gas molecules appearing in the liquid.
Okay.
It's like not a lot of this, right?
Sorry, Maxime, I'm really bad in answering your questions today, but I didn't look into how exactly they extract. But just to follow up on that, how would you explain this anomaly to the extraction efficiencies? You would basically need to have the extraction efficiency should be 20% smaller. It should be around 78 instead of 95%. And how can this, for instance, be? One option would be for some germanium to sneak into the detector so that experimentalists in principle don't know that there's more germanium than there actually is. And we were looking into some cosmic ray interactions producing germanium, and we didn't find the rate to be sufficient. But I can also point out that in one of the SAGE's runs, they put in and they reported to extract factor of few more than they put in. So that never got resolved. It seems like a very difficult task to extract over 100 atoms of germanium from many tons of gallium. So if I were to choose between cross-section flux and the extraction efficiency on the standard model explanations, I would probably bet on this one here. Yeah, none of these three were the most convincing explanations, and the cross-section were already ruled out. But I'm just telling you what needs to happen if I can claim the standard model explanations. If you find this very exotic, that means that it's very hard to explain with the standard model, and then you need to resort to the BSM.
How do they estimate their extraction efficiency?
They're not doing this with this order with smaller number of atoms during the run, but they have some separate stages where they put in some amount of germanium, and they know how much they have, and they kind of in an unbiased way want to extract and see how much they get out. And it worked apparently pretty well because Galax and gallium never reported any problem. But as I said, SAGE in one of their extraction runs, somehow they got 5 times more than they put in. So this is just me giving you a caveat that there is possibly something going on. But admittedly, I never came up with a good way of injecting germanium, for instance, from the cosmics or somewhere. But in principle, you would need to know the one way to solve the problem would be to have more germanium inside than what you actually think that there is. And then I just because I'm already like 5 minutes over time, I just want to very quickly address one of the BSM explanations that we have come up with. And this is basically the analogy of neutrinos traveling to the Earth. When you have these matter effects that we previously talked about, there's been a lot of studies recently with neutrinos talking to ultralight dark matter, which is very big in number density. And you can basically use that as a matter effect. So there would be, it's basically BSM analog of neutrinos traveling through the Earth. This was explored in quite a while, many cases with the usual neutrino phenomenology, but now we want to apply this to the gallium experiment. And basically the solar and reactor constraints on active sterile neutrino mixing are strong. And one way to resolve this is keep it like that and respect those constraints in all the energies, apart from the energies relevant for gallium experiment. There, I want to have the enhancement of the mixing angle induced by this new matter effect. And how this works qualitatively is shown in this plot. This is the electron neutrino survival probability at all the energies apart from this specially chosen energy. So this is the fine-tuned explanation with this enhancement of the mixing angle obtained locally. There's no effect, and everywhere else the solar, I mean, in all the cases the solar constraints are respected. For instance, because this effect here is not reaching the beryllium-7 and pp neutrino range. There are measurement of CNO neutrinos, but those are at the level where only the future more precise measurement can say more and disfavor this kind of explanation. So basically what we did here, we did the tuning and we centered this resonant around the relevant energies for a gallium experiment. And we choose one of these. There are only 4 energies, 4 lines, and this one contributes 80% to all. So this is a very tuned explanation. Yeah. So how can you test this? More precise measurements of CNO, but you can also have new source at best. And they discussed actually zinc 65. So if I put zinc, these lines would be shifted around, and then this would basically be a very straightforward way how to disfavor this kind of proposal. We put out several proposals and summarize the picture of the BSM. This is the proposal from the literature, and here our proposals with star rating from more favorable to less. Interestingly, we also managed to make it work with sterile neutrino interacting with that dark energy, if the dark energy is represented by a slow roll field, because dark energy is all around and there's a big energy density, so you can also use that, couple neutrino to that field. But it's more or less along the similar lines as the one I just explained with the resonant effect. So I'm not going to discuss those in detail. I just want to give you here a survey of possible explanations. So to summarize, yeah, sorry for being almost 10 minutes over. I was discussing the short Baseline Neutrino Anomalies. The MiniBooNE, I hopefully demonstrated that that with the nuclear and hadronic uncertainties, one cannot really explain this 5 sigma effect. You can go to BSM. Sterile neutrino is one option, EV scale sterile neutrino, but the option that doesn't really work with the data. And then with this running effect, we managed to make it more consistent with the data. And I also pointed out that there's also a lot of activities in the non-oscillatory explanations. And the final word will only be given after these presently running experiments are done. They're testing MiniBooNE anomaly, the 3 presently running MicroBooNE, Icarus, and SBND. So we need to stay tuned for the data from those. So that's going to be, I hope to have shed some light on that, but I'm not here to give the final answer on that anomaly. So there's a lot of more data to be analyzed and models to be verified. I briefly mentioned this reactor anomaly. I never really discussed those slides because I skipped, but that one is now fading away, as well as some other reactor experiments like Maxime pointed out, this neutrino 4. And then I spent last 10-15 minutes talking about this a new player gallium anomaly, which is now recently boosted from 2 to 5 sigma. And the explanations within the standard model on the cross-section were already ruled out by the experimentalists. But our explanation on the flux are there, but as you saw, they're in contradiction with the nuclear physics. And there's also the germanium extraction. So again, I just pointed out what needs to happen to have such an explanation. Of course, that would typically induce some other problem. So it's basically maybe research shuffling. And this is also a good driver then to put you in the BSM playground. And for that, we cooked up a model with sterile neutrino, which is fine-tuned but consistent with the reactor and solar and the global data. And this experiment is not as expensive as MiniBooNE. This is my impression as a theorist. So if they repeat this with several different reactive sources and detection material, I'm confident that there could be so much more information to be extracted and that would be a good path toward the final resolution. At least using these different sources and detection material would effectively probe directly all these explanations, SM and BSM, which I discussed here today. So yeah, thanks a lot, and this is all I have to say.
What's the timeline for these experiments? Is the Icarus and MicroBooNE inside? What is it?
So MicroBooNE was installed many years ago, and they're already done with the running, but they put out the first data. What was this date? Maybe I have some. Yeah, there was already a data from MicroBooNE in 2110. I believe there hasn't been anything since from them. They're analyzing, but they didn't analyze everything. Icarus has been taking data for like 2 to 3 years, but informally I heard that they have some problem in understanding the detector. So there hasn't been anything from them yet, but they're working. And SBND was just a few months ago installed. That's the one that is the most massive and the closest to the source. That one, we don't expect to hear from them this summer.
So basically 2 to 3 years is a.
Like I'm not in any of these collaborations, but maybe 5 years is a reasonable estimate for, but yeah, I'm not in position to make any such claims. I mean, you see, hopefully this is a very good program to resolve things, because you see LSND I started with, but I never provided the ultimate explanation. What's currently going on with the LSND is the anomaly that is it's a long-standing one. It's not explained. So hopefully the MiniBooNE will not eventually end up in that business. So we hope to finally, in a very model-independent way to discard. So by the way, what is very good with this experiment and what makes them more powerful, they can distinguish photons from electrons. So at least when you think about the BSM and those kind of explanations, you can distinguish different topologies, and it works much better than, it gives you an extra handle in all of that. And it's also very good that the experimentalists are working on that, because the material here is the liquid argon, the same material which DUNE will use. So, learning about how neutrinos interact with argon is very valuable for the future and the resolution of maybe more important problem like the CP violation in the neutrino sector.
Any more questions? Vedran will be around in Gary, so if you want, Gary to ask more questions. So let's give a big applause to him.
I have a question.
Sorry. Okay, go ahead.
Hey, Vedran. Yeah, sorry for crashing the party, but I had to join your talk.
Yeah, go ahead. Congrats for a job, by the way. I saw you got a job.
Thank you. In this ultralight dark matter scenario that you have, is the reason why reactors are not a problem because of antineutrino versus neutrino, and there being no resonance for antineutrinos?
You're talking about we're in the gallium, right?
Exactly. Yeah.
Ultralight dark matter.
It's not affecting reactor.
The explanation with the resonance.
Right. Or it's only
okay,
energy.
it's certain energy, because we center the resonance is fine-tuned around the 0.8 MeV, which is the 80% contribution. Maybe I can reshare it.
Yeah. So this cares about whether you're a neutrino or an antineutrino, right? Or no?
So yeah, you can choose the sign. You can only have resonance in one of the channels, and we need the resonance in the neutrino. So yeah, you would not expect a resonant effect in antineutrino whatsoever. But on top of that, you also have, yeah, actually that's the resolution for the reactor. For solar, which have the neutrinos, then the width of the resonance is such that you don't enter in the beryllium-7 and PP regime, and then you're fine from that. But for the reactor, it should be neutrinos versus antineutrinos, and the resonance being only in one of the channels, yeah.
And there's nothing else you can do here? Like if I have a large potential for the ordinary neutrinos, I can try to play with the mass splitting and change the resonance condition to higher energies, for instance? There's nothing you can do there?
To get what? To get the effect in reactors?
Yeah, because your resonance depends on the choice of mass splitting, right? So
right.
In principle, I can imagine a standard model potential for ordinary neutrinos. If I play with densities, I can try to match your new potential and change the energy of the resonance around. You see what I mean?
Say it again.
It's just that you can change the energy of the resonance depending on the mass splitting, right? Between your sterile and active neutrinos.
Yeah.
So if I have a potential for active neutrinos, that mass splitting changes. So I can change the energy of the resonance.
But you will also need to change the energies. By the way, this energy is, let me go here. The energy is below 1 MeV. And for reactors, you don't have anything below the IBD threshold, which is like 1.8 MeV, right?
Mhm.
So maybe one option would be to use the coherent elastic neutrino scattering for the reactor neutrinos. But in the usual IBD channel, you would not even expect the events at this place, because the energy from chromium is at 800. You see here 750, and with reactors, there's a lot of flux in that region. But with the inverse beta decay, you don't have you have this gap, right? Difference between neutron and proton mass.
Okay. Yeah, we should chat. Thanks for the talk.
Okay, cool. Thanks a lot.